topic of the next chapter is chemical kinetics. This is an area of chemistry that mainly focuses on studying reaction rates and how reactions occur. In this chapter, we'll discuss how things like concentration, temperature, the actual mechanism of the reaction, and a catalyst can affect reaction rate. First, we'll start with some definitions. So what exactly is chemical kinetics? So pretty much what I said before. It's just the area of chemistry that's mainly concerned with reaction rate. And it's also concerned with the sequence of steps by which a reaction occurs, which is basically a mechanism, a reaction mechanism or a chemical mechanism, which is just a sequence of steps by which reactions occur. So this is how exactly do we get from product to reactant, or from reactant to product, I should say. Okay, so kinetics studies reaction rate, which is how fast can we get there, so how fast do we produce product from a reactant, and the mechanism, which tells us exactly how do we get there. So first we'll talk about some factors that affect reaction rate. So the first one is just the physical state of the reactants. Okay, so do we have two gases reacting with each other? Are they in the solution phase maybe? Are they two liquids? Or do we have two solids reacting with each other? And depending on what state both of our reactants are in, will affect exactly how fast the reaction can occur. So for instance, if I'm combusting a gas, it's a very quick reaction. But if I have two solids in a solid reaction chamber, that might be a very slow reaction. Next, we have concentration of the reactants. So this is exactly how concentrated are your reactants. And this affects things like collisions. So if my two reactants can find each other a lot more easily inside of the solution than compared to if they're very dilute, where they can't really find each other all that often, that's going to affect the reaction rate. So slower or faster, just depending on the particular reaction. Generally speaking, if two reactants can find each other more often, that's going to be a faster reaction. Okay, next we have temperature. Okay, so we can study how fast the reaction goes to completion by varying the temperature. Do we have a high temperature or do we have a lower temperature? So are we below freezing for that liquid or something like that? That's going to be a very slow reaction. Or if we heat the reaction, generally speaking, that will give us a quicker reaction. Not always, but most of the time. Next one would be a catalyst. So a catalyst not only speeds up a reaction, but most of the time it actually unlocks a different pathway. So a catalyst can actually unlock a reaction that isn't necessarily possible without it. Okay, so it can open up a different pathway, which will sometimes be a lot faster, or sometimes won't even be possible without the catalyst. Okay, so let's get into reaction rates. So what exactly is a reaction rate? So this is just a change in the concentration of the reactants or products per unit of time. So we have that our rate is just equal to, so our concentration over time. And this can be the concentration of either the products or of the reactants. So it can be measured as either the increase in the products, so our products will always increase since they're growing in. We're starting from no product and we're forming product, so that's an increase in the product. Or the decrease in a reactant. So if our two reactants are reacting with each other to form the product, obviously they're going away. Okay, so if we're talking about the reaction A goes to B, we can write some general reaction rates. We can say that rate is either equal to the change in the concentration of B, which is our product, over the change in time. So this is just very, very general reaction rate. Or I can look at the reaction to say that it's the negative, in other words, the disappearance, so the change in the concentration of A over time, and again, it's negative because it's going away. So if I'm talking about the reactants, I have to throw a negative sign in there because they're disappearing. And generally speaking, they'll be expressed as molarity per second, not always. This may be something we haven't looked at before, but if we have these square brackets like this, okay, so the brackets on either side, generally represents molarity, but it can also just be used to mean concentration. But generally speaking, if we have square brackets, we're talking about molarity. Okay, so here's just an example reaction. So we have N2O5 decomposing to give us NO2 and O2. Okay, so we're going from a colorless gas to give us a brown gas and another colorless gas. And what we have is we have some time measurements. So you're using a stopwatch or something like that. And then we have concentration measurements. And there's different ways to measure certain concentrations within a reaction, such if you have a colored species, you might use a spectrometer to measure that. But there's other ways to measure concentration as well. Right now, that's not so important. Just understand that what we've done is we've measured the concentrations of our reactants and our products over time. And these are given in molarity. So we're starting from 0.02 molar of N2O5. Okay, and that's at time 0. So before anything happens, this is how much N2O5 we have. And notice that our two products start from 0. So at time 0, we have no product. And notice what happens over time. So from time 0 to 100 seconds, we lose some of our reactant. And now we've gained some of our products. Notice we haven't gained equal concentrations of our products, so that'll be important later. Okay, but just understand that as we are going from time 0, time 100, we've lost reactant, gain product. When we move another 100 seconds, we lose even more reactant, gain even more product. Okay, so note that the concentrations of NO2 and O2 increase as the concentration of N2O5 decreases. So as our reactants are going away, our products are increasing. If we take a look at a plot of the same data, what we can see is in the purple line we have the N2O5, in the green line we have the NO2, and in the blue line we have the O2. Okay, so here we're plotting concentration versus time. Okay, so we can take a look at how things are decaying and how things are increasing. Okay, so the purple we see the decay rate for our reactants. Okay, so over time, our reactant is going down, it's decreasing. At the same time, we're increasing NO2 and we're increasing O2. Okay, so what we can look at with this is we can look at that at different points in the reaction, the rate is different. So at different points, if we were to measure the instantaneous rate of the reaction, we would get slightly different rates. Okay, so in other words, the rate of decrease here is not necessarily as the rate of decrease here. The rate of increase here is not necessarily the same as it is here. We can also see that the rate of increase of N2O5, or sorry, the rate of increase of NO2 is not necessarily the same as the increase of O2. But what we can do is we can look at different points on the line and we can measure the concentrations or find the concentrations and look at the change in those concentrations over a set period of time. From that, and I mentioned this earlier, we can get instantaneous rate. So that's, in other words, the rate of the reaction at that specific time. Right now, let's just focus on the idea of decreasing product, decreasing reactant, increasing product. Okay, so it says the slope of the hypotenuse of each triangle gives the average rate of change of the product or reactant concentration during the indicated time interval. In other words, taking the slope of the line, essentially, will tell you the rate at that given time interval. So we can measure something like the rate of decomposition of N2O5 at a given time period. So remember we wrote these general reaction rates before. So we said the change in the concentration of N2O5 over delta T, and we said this was negative since it's decreasing. If I take a look at that, it will tell me the reaction rate at that particular moment during the reaction. So here we have an example going from 300 seconds to 400 seconds. And my concentration changes from 0.0120 to 0.0101. Okay, and remember, I'm talking about a delta. So what do I care about? I care about where I ended up and where I started from. Okay, so it's the final concentration minus the initial concentration. And same thing for my time. So 400 seconds minus 300 seconds. So in other words, a span of 100 seconds. But notice my actual reaction rate, if I subtract these two numbers, I end up with a negative sign. And I also have a negative up front. Okay, so if I do this math, I come up with a positive number, 1.9 times 10 to the minus fifth molarity per second. So what is this telling me? Why is it positive? Why is it negative? I said before that these needed to be negative since it's going away. Well, what this tells me is that the rate of decay of my reactant is 1.9 times 10 to the minus 5 molarity per second. Okay, and your reaction rate always needs to be a positive. But you have to understand what that tells you. So it tells you still the rate of decay. It tells you the rate that it's going away. So what if instead I wanted to look at the products? So we know that the products are increasing, they're growing in other words. I can set up my same general reaction rate equation, so the change in the concentration of the product over the change in time. And I can set up the same calculation, again, final minus initial, final minus initial. Okay, and I get 3.7 times 10 to the minus 5 molarity per second. And again, it's positive. Okay, so the rate of ingrowth of NO2 is equal to 3.7 times 10 to the minus 5 molarity per second. That's how we would read this. And I can do the same thing for O2. So same setup. And again, I end up with a positive 9 times 10 to the minus fifth molarity per second. Okay, so same process for all three of these. And what that tells me is that any individual moment, so for any individual time span during the reaction, this was my average rate for that either ingrowing of the product or disappearance of the reactant. So there's one thing I haven't quite mentioned yet, and that is the reaction rate as it pertains to stoichiometry, or stoichiometry as it pertains to reaction rate. So your stoichiometry of the reaction actually affects our reaction rate laws. So we'll get to writing more complex rate laws in a moment, but still sticking with our just general rate equation, we have to also consider our stoichiometry. And we'll do this in the form of adding a fraction in front of our general rate equation. Okay, and this just comes directly from the reaction stoichiometry in the equation. So here you see I have a 2. So this becomes 1/2. A 4, 1/4. Here we just have a 1, so this stays as a 1. Okay, so this is the new form of my general rate equation, which for a general reaction looks something like this. So if I have A of A plus B of B giving me C of C and D of D, I can write these general reaction equations, or rate equations, I should say. Okay, so again, keeping my negative sign for my reactants since they're disappearing. So I'm going to be 1 over little a, which where little a is my stoichiometric coefficient, times change in concentration of A over the change in time. Same thing for B. Then C and D, since they are products, the only thing that changes is they don't have a negative sign. Okay, so without knowing anything else about the reaction, aside from the change in the products or the change in the reactants and the actual equation, this is the rate equation I can come up with. Okay, so I can just give a general form of the rate equation, and that will tell me the reaction rate at that particular span of time. Okay, so here's one for you to try. I just want you to write a rate expression that compares the disappearance of the reactants and the formation of the products for the following reaction. And they tell us that we have pH3 decomposing to P4 and 6H2. Okay, give this one a try. See if you can just write one of those general rate equations for it. Okay, so with this one, they just want us to write this type of rate. So they want us to say rate, let me try that again, zoom in a little bit too. So they just want us to say rate, and remember this general form of just 1 over A times concentration of A over delta T. So they want us to write something like this. Okay, so just this very general form. So what we'll write is, we can say that rate is equal to, and we'll start from our reactants. So we'll start minus, since our reactants we know are going away, and our 1 over A here will be 1 over 4, and that's just coming straight from the stoichiometric coefficient. Okay, times the concentration of pH3. Try to draw that a little bit neater. Over delta T. Well, we don't know what the delta T is. They didn't tell us the delta T. And that will be equal to, so what do we have? We have just 1, so we don't have to write anything. Concentration of P4 over same concentration. Change in time, which is equal to 1/6 concentration of H2. Sorry, these should be delta. I forgot to put in the delta there. Over delta T. Okay, and that's really our whole answer. There's really not much else to say here. Okay, so just a very general rate expression. Okay, so if we take a look at a plot of some data for this reaction, so the same N2O5 reaction, what we can see are several different ways of determining the rate. So if we want to know, for instance, the initial rate, we might look at the tangent at time 0. Okay, this tells us an instantaneous rate, and in this case it's the initial rate since it's at time 0 for the reaction. But it only tells us the rate at that specific moment in time. Same thing if we were to look at time, for instance, 350. So t is equal to 350 seconds, so that would be about here. So we can take the tangent at that point, and again, it will tell us the instantaneous rate at that particular moment in time. But what we can see from this graph is that the rate is not consistent through the entire reaction. In other words, the rate here may be not the same as here or here. So to get a more accurate idea of the reaction rate, we may want to take what's called the average reaction rate, which is what we were just doing before. So we were looking at delta T and delta concentration. Okay, so the wider we look, so if we look over a very wide time span, so T is equal to, here it looks like, what, T is equal to like 600? Or a change in 600 seconds or 500 seconds. So a change in 500 seconds for the purple. Okay, so this gives us a better idea of the average rate over the entire reaction. And the more narrow and narrow time frame we look in, the more we're talking about the reaction rate at that particular moment. So the wider time span we look at, we're getting a more average reaction rate. The more narrow a time span we look at, the more instantaneous we're looking. Okay, so what if we have concentration data like this? So this says that it's data collected on the concentration of a dye as a function of time, and that's given in the table. And ask you two questions. It wants to know what is the average rate of change of the dye concentration over the first 2 minutes. And then it wants to know what is the average rate of change between minutes t equal to 4 and t equal to 5. Okay, so use those same general reaction expressions and see if you can answer these two questions. And we'll go over them together. We don't know a whole lot about this particular reaction. They didn't give us a reaction equation. They didn't tell us any stoichiometry. So we're just going to have to kind of make some assumptions. So let's start out by just saying our rate will be equal to, and we don't know our equation, so we're not sure if we have any coefficient up front, but what we do know is we're talking about decomposition. So I know it's going to be negative change in the concentration of our dye over the change in time. Okay, and that's good enough to answer this because they don't give us any more information than that. So we can say the rate for the first 2 minutes will be equal to minus change in concentration. Okay, so in this particular case, we're looking at the first 2 minutes. Okay, so we'll say 1.7 times 10 to the minus 5, and that's molarity minus, and then our initial concentration, 3.4 times 10 to the minus 5 molarity over our change in time. Okay, so what is our change in time over 2 minutes? And we want this in seconds so that we have our answer in molarity per second. Well, 2 minutes is 120 seconds, of course. So this gives you an answer of 1.42 times 10 to the minus 7 molarity per second. Okay, so it's easy as that. For the first 2 minutes, that's our average rate. Okay, so now the second question, so this was answer number 1. What about number 2? So now they ask us between minute 4 and minute 5. So that's here. So same thing, rate equal to minus, because we're still decomposing, and our final concentration will be 0.6 times 10 to the minus 5 minus 0.9 times 10 to the minus 5. And those are both in units of molarity. Okay, and this is going to be over our delta T. So this part we have to think, what's our delta T? Okay, we're not starting from 0. We're only looking at 1 minute. Okay, so our delta T will just be 60 seconds. And if you solve this, your answer comes out to about 5 times 10 to the minus 8 molarity per second. Okay, so that would be our two final answers. Okay, and that just tells us the average rate of the reaction at that point in time. So based on the information they gave us here, that's really the best we can do. Okay, so I think that is a good place to break up this video. So when we come back, we'll look at concentration and rate laws.